Welcome to lab number 4. Today's lab deals with compliance and Hooke's law and other topics from chapter 4 of the textbook. But before we do the lab, I'd like to put it in perspective. Today's lab is going to give us the second of 4 equations we need for the major project, and I'll come back to that in a minute. Today's lab is going to deal with elasticity of different organs inside the human body. If that organ happens to be a compliant blood vessel, something that has pressure and volume, we use the compliance equation 412, which says that the pressure inside that vessel is equal to the excess volume over the residual volume divided by the coefficient of compliance. But if the organ we're interested in is a more rigid organ, like the bone or a ligament or a tendon, then we use Hooke's law, where Hooke's law says that the stress, which is again force divided by area applied to that organ, is equal to Young's modulus times the strain, which is the normalized change in length of that organ. And that's equation 4.3 in the textbook. We're going to apply both of these equations today in today's lab. Actually, I like to think of these two equations as brothers, because they have a lot of similarities between them. Let me point out some of those similarities. On the left-hand side of each is force divided by area, pressure, and force divided by area, which is stress. Another similarity is on the right-hand side, we have excess volume over residual volume. Here on the right-hand side is strain, which is the change in length divided by the starting length. Another interesting comparison between the two is they both have coefficients, coefficient of compliance and Young's modulus. However, there's distinct differences between these two brothers. They are not twins. They have very much different personalities. In fact, I like to think of this equation as maybe being someone who's gone to the East Coast and become a lawyer, and this equation is someone who got their education on the West Coast and became, let's say, a minister, because they do have distinctive different personalities. Let me explain the differences. The force in this equation for pressure is outward against the walls of the vessel, whereas the direction of force in stress is along the length of the organ. Another big difference between these two equations is the location of these coefficients. The compliance coefficient is in the denominator of this equation. Young's modulus coefficient is in the numerator of this equation, and that makes a huge difference. For example, for Young's modulus, let's think about whether a very stiff organ would have a high Young's modulus or a low Young's modulus. Well, it actually is a high Young's modulus. The stiffer the material, the larger is Young's modulus of elasticity. That's because for a given strain, it takes a lot more force for a stiff object, and therefore Young's modulus is a lot bigger. In fact, I actually like to think about it as Young's modulus of stiffness, because the more stiff the material, the higher the Young's modulus. It's just the opposite here with compliance. Notice the compliance is in the denominator. That means that a very soft vessel has a large compliance. Compliance is actually a good word to use for this coefficient, because the more compliant something is, the softer it is. And then there's one more difference between these two equations. Usually Hooke's law is done in units of SI units, whereas traditionally compliance is done in clinical units, and that's what we'll do for the major project. So, returning back to the major project, we now have 2 out of the 4 equations needed for the major project. The first equation we dealt with last week's lab. That's Poisson's equation. This is the simplified version here. This week's lab deals with the compliance equation, and we're going to apply both of those equations to the blood vessels around the systemic cardiovascular system. We're going to have to find the resistance for each of those vessels, and we're going to have to find the compliance for each of those vessels. We'll do those in a later lab. Oh, incidentally, the third and the fourth equations are the conservation of volume equation, and Euler's update equations. We'll deal with those in a later lab. Now, on to today's lab. For the first part of today's lab, let us make some measurements that will allow us to calculate the compliance of an artificial vein material that I have here. Even though this is an artificial material, it has a lot of the similar properties as a real vein. Notice how flexible it is. The wall thickness is quite thin, and the diameter is about the same as a vena cava. I've laid out a length of this artificial vein material here on the table. We have water to represent blood, and notice that I'm measuring the pressure inside the vessel with this pressure gauge. Right now the pressure is at 0, but there's still some water inside of that vessel. That water that's inside the vessel is known as the residual volume. The definition is the amount of volume that's left in a vessel even though its pressure is 0. I've measured this volume earlier, and it's 110 milliliters. Put that down on the worksheet as the original volume and the residual volume. Next, what I'm going to do is I'm going to use this hand pump to pump some water from this beaker into the vessel, and I'll measure how much water it takes to raise the pressure inside that vessel up to 5 psi. Let's do that now, watching the level of the water in the beaker. Okay, I'm up to 2 psi, 3 psi, 4 psi, and now I'm at 5 psi, and I noticed that it took 100 milliliters of water in order to raise the pressure up to 5 psi. Mark those numbers on your worksheet. You'll have to convert the 5 psi to clinical units of millimeters of mercury. And from all those numbers, you'll be able to calculate the compliance of this artificial vein. And you should get a number that's between 2 to 6 times 10 to the minus 4 liters per millimeter of mercury. Now let's do the Hooke's law portion of this lab. Here's the apparatus that we'll use today. You're going to make a sketch of this apparatus on your worksheet, just the major parts, and label each part for a record. We have a ring stand here, and from the top of the ring stand I've attached a rubber band, and that rubber band is going to be our artificial tendon that we're going to find the Young's modulus of. Of course, it's much more flexible than a tendon, but it will do for our purposes today. At the bottom of this rubber band, I've taken a paper clip and formed it into a hook. And on that hook, I will place an empty Coke can. Why did I make a hook out of this rubber band, out of this paper clip? Because we're dealing with Hooke's law. And notice that the Coke can is RC Cola. RC has a big, important role in the lab this semester. Well, I want to add various amounts of water to this Coke can, and for every increment of water, we will measure the increment of how far the rubber band has stretched its length, and we'll measure that with a ruler. Now, how many increments of water do I want to put into this Coke can? Well, I noticed that it's empty at the start, but it contains 355 milliliters when it's full. So if I put in 50 milliliters of water for each increment, then that would take about 7 increments to completely fill the can, which I would like to do because that stretches the rubber band as much as possible. Before we get to that point, though, we need to make a measurement of the cross-section, and that is the end of the cross-section of the rubber band. Why? Because that is the area through which the force is acting on that rubber band. It is the cross-sectional area in this direction, the cut area of that rubber band, and I measure it to be 6 millimeters by 1 millimeter. Please mark this down on your worksheet. You're going to need it later when we calculate Young's modulus. Well, As I start to fill this can, we're going to need to record both the volume that I put in the can and the incremental length between those two marks there. Let's see on the worksheet where we put that. Well, this is the first worksheet of today's lab, and up here at the top you will have already filled in the values for these quantities that allow you to find the compliance of the artificial vein in clinical units. In this region here, you draw a sketch of the apparatus that we use to find Hooke's law for the rubber band, along with the dimensions of the cross-section of that rubber band here. And in this region, this is where we're going to enter in the various data points that we're next going to measure. You know that for all plots and tables, we need a title here. Put a title in there of your choosing. And we have two variables to record: the volume in units of milliliters and the length between the lines on the rubber band in millimeters. We're going to start out with 0 volume. That's our initial point, 0 volume. And then we're going to add 50 milliliters for each successive measurement up to a maximum of 350 milliliters. As we make the measurements of the length, I want you to enter in the values in millimeters for each of these measurements in your table. Now let's collect some data points for our stress versus strain curve for this rubber band. The first data point is actually with 0 weight on the rubber band. Now I know this Coke can has a little bit of weight, but it's so light when it's empty that I'm going to ignore that weight, call it 0. And the length at the first data point with 0 weight is 63 millimeters. L is 63 millimeters for 0 weight. Now let's add the first increment of water. $50 milliliters. And the length is now, between the lines, is now 67 millimeters. 67 millimeters. That's with 50 milliliters of water. Next data point. Well, this data point has 100 milliliters of water, and the length between the lines is 70 millimeters, 70 millimeters. Let's do the next data point. This is for 150 milliliters of water, and the length between the lines is 76 millimeters. L is 76 millimeters for this data point. Next data point. This data point is for 200 millimeters of water, and the length is 83 millimeters. 83 millimeters. Next data point. This data point is for 250 milliliters of water, and the length between the lines is 91 millimeters. 91 millimeters. Next data point. This is for 300 milliliters of water, and the length between the lines is 100 millimeters exactly. And now for the last data point. This data point is for 350 milliliters of water, and I can tell the can is almost full. And the length between the lines is 111 millimeters. 111 millimeters. Please mark that down on the worksheet. Now that we have all the data points, let's let MATLAB plot out a graph of stress versus strain. But first we need to put down a few equations that we're going to enter into MATLAB. Let's do that now. So on the bottom of the first worksheet, let's write some equations that we're going to need to write the script for MATLAB to solve and to plot the stress-strain curve. Let me just insert one from last lab, which is the equation for the force in terms of the density of water, the volume of water, and the acceleration of gravity. That's from the last lab. I'm going to let you write these other equations here from the various equations in the textbook. Let me just point out one thing, that instead of using a lowercase l for length, I have chosen to use an uppercase L, because the lowercase l in MATLAB script fonts looks a lot like a 1. So let's use an uppercase L. Now let's turn to the second worksheet. On the second worksheet, we're going to enter in by hand the lines that we will later type in as a script into MATLAB to allow MATLAB to solve for Young's modulus. Starting first with the vector called L of all of the lengths that we've measured. And we're going to enter them into MATLAB the same way we did in lab number 1, inside of square brackets, starting first with the first value, which was 63, and then later values here separated by either a space or a comma. Now, MATLAB doesn't keep track of units, but I would like to remind myself what this vector represents and what the units of that vector are. So I've entered a comment. A comment is anything that follows a percentage sign in the MATLAB script. MATLAB does not execute this, it merely displays it to remind you what this vector represents and what its units are. Going on to the volume vector, there are 3 different ways we could enter the volume vector in. First, we could use the same square brackets that we used earlier, starting first with the first volume, which was 0, and then incrementing by 50 inside the square brackets. And I put a comment here to remind me that this is volume with units of milliliters. But there are 2 other ways that you could enter that volume vector in. We could use the colon operator that we've seen before, starting first with the very first value of volume, which is 0, incrementing by 50 for each increment, and ending in 350 milliliters. That's one way of doing it, and that's going to give you the exact same vector that you get from the previous line. Or if you're adventuresome, you might want to investigate a third way of making the volume vector called linspace, which stands for linear spacing. And inside the parentheses of the linspace command are 3 entries separated by a comma. And those 3 entries I will let you look up in the help section of MATLAB to see how you'd put values in there which would allow you to generate the very same volume vector that either of those 2 ways of entering it are. You can use any of these 3 ways to generate the volume vector for this week's lab. Going on, we need an equation for force, F. And I remember that force was density times volume times acceleration of gravity. From now on, I'd like to put things in the SI system because our eventual Young's modulus is going to be in the SI system. So from now on, I want to put in values that are SI values. Well, the density of water, I remember, is 1,000 kilograms per meter cubed. I'm just going to put this up here to remind me what the units are there. That's volume, that's density, times volume. Well, the volume V is the row vector that we just generated by any one of these 3 methods just above. And that is in units of milliliters. And then we're going to multiply that by the acceleration of gravity, which is 9.8 meters per second squared in the SI system. But now I'm going to need to convert that from milliliters over to the SI unit. And I'm going to let you determine what goes for the rest of this line to convert these values over to SI values. Make a comment to myself that this is force, and it should be in the SI units of newtons. Now, for this conversion that you're going to put in here, you're going to divide or multiply by 100 or 1,000 a couple of times or something like that. You could put in, to finish out this line, 1,000 if that's what you're going to multiply by. But let me remind you that there's a slicker way of representing 1,000 in MATLAB. 1 times 10 to the third power, 1e to the 3. And that's especially helpful if you're going to divide by 1,000, because dividing by 1,000 becomes 1e to the negative third power. So that's a slick way of putting in these conversion factors. You do not have to type this into MATLAB, just to remind us what those values are. Going on, for area, use the measurements we've made of the cross-section of the rubber band to put in values there to allow you to calculate area, make a comment here, in units of meters squared. Make sure you put that in units of meters squared there. Oh, and keep 2 significant figures for area. Now for stress, stress is often given the Greek letter of sigma. But there is no sigma on the keyboard. So we have to label that vector with some other label. You could type in sigma here if you'd like. I've actually made the variable stress because that's what it actually is. Then put in here by hand an equation from the previous worksheet which represents how you calculate stress from some of the previous variables we've used. Make a comment here and put units in the comment. I'll let you figure out what the units are and put the units in a comment there. For strain, often that's given the Greek symbol of epsilon. No epsilon on the keyboard, so I've actually let the variable name be strain. I'll let you from the previous worksheet put in the equation here for strain, and in the comment put down what its units are, if it does have units, right there. Oh, I remember from the strain equation that it actually employs L sub 0, which the textbook calls L sub 0, which is the very first value of length. Well, here's the first value of length, and you could type in to that equation 63. You could hard code it as 63, but there's a more elegant way of doing it. Let's let MATLAB find that first value of length, and MATLAB calls that L parentheses 1, the very first value of length. Now, even though the textbook called it L sub 0, MATLAB does not allow 0 to be an index number. It always starts with 1 as opposed to Python and C++. So the very first value of L is L parentheses 1, and to be elegant, you could put that into your equation for strain. Now going on, you've plotted before, and you know that the very first variable that you put in here is plotted along the horizontal axis, and the very next variable that you put in here is plotted along the vertical axis. We want to plot stress versus strain, but which one of those you put in here and which one you put in there, I'll let you decide that by looking at the textbook, which one's horizontal and which one's vertical. And then after that second comma, let's customize the plot with a single quote, and what we're going to do is change the color and change the marker style and change the line style of that plot according to this table that you will use a lot in the major project. This table is also found in a slightly different form in the help section of MATLAB. And notice that by giving different symbols, you can change the color of the lines, you can change the marker style, and you can change the line style of the plot. I would like to make my plot with a dashed line, which are 2 dashes here, with a square as the marker style, which is an S, and I'm going to choose green for the color. And so to do that in any order, and you can use 1, 2, or 3 of those symbols in any order, you put those in single quotes as the last part of the plot command. And I wanted to use a dashed line, which is represented by 2 dashes here, a square, which is an S, and a green line, which is represented by the letter G. Close the single quotes and then close the parentheses. Now for your particular plot, I'd like you to use a different line style and color and marker than I've used here. I'll let you decide which ones you want to use. Just use something different than my values here. Going on, we will have to put a title on this plot, and you know how to do this. Put it in single quotes inside of the title command here. Put on a label for the x-axis in single quotes here, and put on a label for the y-axis in single quotes here. Put units into these labels if it does have units. And then put a grid on the plot. Type those lines in and save it as a new script in MATLAB with a name of your choice here. And then run it. And from the figure, you'll use the cursor to find the approximate slope of the upper 2/3 portion of the curve, and that will be Young's modulus, which you will record right here. Let me show you how to do that next. When you open up MATLAB on your machine, you'll get a desktop that looks something like this. We want to enter a new script into MATLAB, and we do that in this upper tool strip by clicking on to the far left the icon that says New Script. That opens up an editor, which is like a word processor, and here you're going to type those lines that you've written by hand on the worksheet. But I'm actually going to do something a little bit different to illustrate some things. I've made up a pretend program that I'm going to cut and paste into the editor, and this pretend program displays the number of free throws, consecutive free throws, that a basketball player might make depending upon how many hours that they put in to practice that. The free throws I've entered in with square brackets in the normal way. The hours I've entered in using the colon operator, and I'm going to plot those pretend free throws in a row based upon the number of practice hours using a solid line, a solid blue line with asterisks as the marker. I've titled that plot, and I put labels on both the X and the Y axes, and I'm going to put a grid on the plot just like you will. Now we want to save this script. We do that in the upper tool strip again by hitting the save icon right here, and up comes a dialog box that will allow us to enter in whatever name we want to save this script with. You choose whatever name you'd like. I'm going to choose the name Free Throws for my script, and when I hit the save button, it saves over here in the current folder, freethrows.m. This is an M file, which is the script that you can run as many times as you'd like. Now to run this, there are two ways to do that. The first way is in the command window, you type the name of the script, free throws here, without the .m. And then when you hit return, it's going to run. But before I do that, let me explain that I purposely made a mistake here in the editor, such that when I run this now, I see that mistake, up comes the figure, but it's not been complete, so I'll get rid of that. And the mistake I made was that I have mistyped the name X label. It's B-E-L, not L-E. It's not table, it's label. Let me correct that in the editor. And the reason I made this mistake is to show you that typing something into the command window is different than typing it in as a script. If you type that into the command window, the lines are executed immediately, and you'll see the error immediately. In a script, you won't see the error until you actually run the script. But then, it's easy to go back into the editor and correct it. Now we want to run this script again. So I'll show you the second way to do that. In the upper tool strip is this arrowhead here. If we push on that, it's going to both simultaneously save the current version and run it. So let's do that. And up comes the figure. Now this figure looks a lot like the figure you're going to get for your rubber band. It has a steeper slope at the beginning, And then the second 2/3, the last 2/3 of the curve are sort of Hookean, sort of in a straight line. Let's assume it's a straight line. And we need to find the slope of that line to find Young's modulus. And as you know, the slope is rise over run, or delta y over delta x. The way we can get delta y and delta x, there's a trick here. Let's go up to the Tool tab up here at the top, pull down and select Data Tips. You can also get it right here in the figure by selecting that icon. And what that will allow you to do is to click on any of the data points, and it will give you the x and y coordinates of that data point, x and y. You can do that for the upper point, and then down here, maybe this is where the upper slope looks like it's sort of Hookean. Let's click on that, and that will give you, again, the x and the y values for that data location. And that will allow you to get delta y over delta x to find that slope. You'll do that to find Young's modulus. You'll get a value somewhere between 0.1, 0.1, and 0.8 megapascals. Please do that and record that value on your worksheet to turn in. But you also will need an explanation in molecular terms of why the rubber band has a steeper slope before it sort of turns into a straight line here. Think about that and answer that question on the worksheet. Now we'll want to save this graph to turn in with our worksheets. And the way we save the figure here is up under the File tab in the Figure window. Come down and select Save As. And it'll ask you what title you want to save the graph as. I'm going to save it as Lab 4, and then put my initials. We'll do that in the major project a lot, so that if something gets lost, we'll know who it belongs to. And I'm going to save that as a PDF format. You have a lot of different options here, but let's save it as a PDF format, because that's how we'll turn it in with our worksheets. We save it, and over here, in the current folder, that PDF file is saved. This is where you'll retrieve it to turn it in with the 2 worksheets that you'll turn in to complete today's lab. Well, I hope you've learned something about elasticity and MATLAB with this lab, and I look forward to seeing you in the lab next week.